To everyone. First of all, I want to thank the organizers for this opportunity to show what we have been doing for the last few years. And today what I'm going to talk about is two-dimensional magnets. Now this is a domain of research field. This is very active right now, so I don't have to say much about this in the introduction. And thanks to Susmita also, she has introduced certain concepts very nicely so that I don't have to repeat them. I will highlight two things here in my talk. One is intercalation. Now this has become certainly an important point actually. I will be talking about van der Waals magnets where the layers are coupled to each other by weak van der Waals forces and there is a van der Waals gap there. So now the question is that if the magnetic atoms start to go inside these van der Waals gaps, what will happen? What are the consequences of that? So I will highlight something there. And then also proximity effects. This is nothing new, but also in a van der Waals heterostructure where there is no chemical bond between adjacent layers, what happens due to proximity effects? Can we expect to see something exotic? So first I want to acknowledge all the people who have contributed significantly. So in the first row, a bunch of PhD students and postdocs. And also I want to greatly acknowledge the experimental collaborators, Soroj Das and his team in Chalmers, and Marcelo Lopez in Berlin. I will show some results from them. Just a few words about 2D magnets and their heterostructures. This field has started around 2016, 2017, not very old. There was a standard concept that if you have a two-dimensional magnet, that you cannot stabilize the magnetic order at a non-zero temperature if you have isotropic interactions. Now, it was found out that this magnetic anisotropy is the key factor in establishing, in breaking this symmetry, there is isotropy, and basically establishing a long-range magnetic order even in a monolayer two-dimensional magnet. So traditionally, the first ones which were discovered is chromium I3, which is a ferromagnetic insulator. Unfortunately, the Curie temperature is pretty low in the monolayer regime. It is around 45 Kelvin in bulk. It is 60 Kelvin. Nevertheless, it shows very, very interesting physics. And then started the evolution of some metallic ferromagnets. There, the Curie temperature of these metallic ferromagnets, they were pretty high. Specifically, you see this iron 5 germanium telluride. These metallic ferromagnets have room temperature close to, have Curie temperature close to room temperature, and even if you can increase them by alloying. So there are some papers where they have shown that if you alloy with cobalt or nickel, you can actually increase the Curie temperature to a very high value, like even 550 Kelvin or so. So one can understand that this field is very interesting if you can have a high temperature, room temperature or above material which has a nanoscale dimension, and this can be extremely important for devices and things like that. So specifically the two-dimensional metallic ferromagnets, people talk about these iron germanium tellurium systems a lot, and some vanadium selenide systems, and there are also some new systems which have also come into play. Now not only just the 2D magnets, but their interfaces. So interface is always discussed in detail because that gives us a lot of surprises. So the interface tuning and interface coupling, when you have two different magnets or two different two-dimensional materials in proximity, they can show us very interesting properties, and these properties can be tuned by different ways, like strain effects or hybridization, or even the proximity of spin orbit coupling, dielectric function and things like that. So there's a huge playground with two-dimensional materials in their heterostructures where you can influence one material by the presence of the other. So today I thought about talking about certain things. First of all, I will talk about this iron 3 germanium tellurium systems a little bit, doped with nickel. This work is driven by an experimental work from Berlin. Then I will show some theoretical predictions. I will show that how you can actually think of forming some skyrmions in this iron 3 germanium tellurium systems. Now this is a centrosymmetric system where we do not expect to see skyrmions. But nevertheless, some experimental groups, they have observed skyrmionic features in iron 3 germanium telluride. The reason is not entirely known exactly from where it comes from. There are different theories about this. But we thought to actually make a heterostructure and see, look at certain scenarios and see whether there is a particular scenario where you can actually observe skyrmionic features. Because to observe skyrmionic features, you need to have a very, very critical balance of different parameters in your spin Hamiltonian, which is very, very critical. And then I will show some high throughput study of certain new potential two-dimensional magnets of this kind of chemical formula. Now all these things, they have been studied with density functional theory as the base point, as the base methodology. And then you can go to different flavors. You can go beyond standard density functional theory to include the Hubbard corrections in different flavors. You can use a static mean field way or dynamical mean field way, depending on what do you want to do, what you want to show. And when you have done DFT calculations, you can map that into spin Hamiltonian. I'm sure you have heard this in many talks here. A spin Hamiltonian can be very long. The essential spin Hamiltonian that we usually use, they are given here, the isotropic part, which is this part where the parameter that we calculate from DFT calculations, DFT or beyond, is these Jij parameters, pair exchange parameters. The Zaleshinsky-Moria interaction parameters, we also do extract these things from ab initio. And then the anisotropy parameter Ki, that is also very important.
In Sweden, do they write E in place of S for the spin?
No, these are unit vectors. Now, the value of the spin moments there. This is one way of representation. Okay. So this is this, but you can extend the spin Hamiltonian to any extent. Whatever you can make it longer, and you can use dipole-dipole interactions and all different things. So basically what we want to calculate is a generalized 3x3 exchange tensor, and this tensor we can actually have the relativistic treatment included here, and also if you want to have the dynamical correlation, that also can be added in the same footing, and it is a closed form of this Jij tensor. This J tensor can be written like this, where you have both the self energy that is coming from the electron correlation, and then you have this spin orbit coupling that gives the non-diagonal part of this J tensor. Once you have all these parameters extracted, you can use them in Monte Carlo simulations, or you can use them in atomistic spin dynamics simulations, or further you can use it in micromagnetic simulations, depending on what you want to study.
Are they classical spins or quantum?
These are classical spins.
Sure. Otherwise, you have to do quantum Monte Carlo.
No, these are classical spins. That is one of the simplifications that we use. But the kind of problems that we deal with are they're very complex problems. So these are the only solutions you can have. So now what I want to say is that this intercalation of these magnetic atoms in these systems, recently there is a paper I just want to highlight from Stuart Perkins' group. They have shown this. If you have this iron 3 germanium telluride systems, then you can see so this is basically the system. These are the monolayers. You have the tellurium atoms, then you have some iron atoms, germanium atoms, and then there is a van der Waals gap here, and then is the second layer comes in. This is a typical bulk unit cell of iron 3 germanium telluride. But what you see, what they have shown, that there are iron atoms in the van der Waals gap. Now, they have convincingly, they have shown some charge density difference maps, and then from there they have shown that okay, these iron atoms, they in the van der Waals gap, they sit in certain symmetry sites, and then the rest of the parts are empty. So this is a two-dimensional layer in the van der Waals gap where there is a dilute iron atoms. They are sitting with a binary alloy of iron and vacancies. Very interesting, but the story doesn't finish here, because they show that they claim that they see some spin glass behavior if you have iron atoms in the van der Waals gaps. And the microscopic picture is not known, and but the experimental observations, they show a frequency dependent shift of this AC susceptibility, and that from there they say that this is a realization of a two-dimensional spin glass phase in this kind of van der Waals magnets, which is very interesting, and a lot of things have to be understood here. Nevertheless, my system is similar to this. What we have so we have iron germanium telluride, but we have nickel doping here. So our experimental collaborators, they have synthesized this material by molecular beam epitaxy in Berlin, and I think this is too much for Okay, so they have this pristine I call FGT a short form. So they have this pristine FGT, and they have this nickel doped FGT shown by two different ways. And what you see that this nickel doped FGT, there are nickel atoms here in the van der Waals gap. So if you dope with nickel, you see that the lattice parameters, they change. The A lattice parameter and the C lattice parameter, that changes with nickel doping. And I will just highlight certain things, not go into experimental details. But if you do this HARDF and this particular experiment IDPC, so you see that there are actually, they see the signatures of these atoms in the van der Waals gap. And if you go further, and they have done several measurements, magnetic measurements, bulk squid magnetometry, and also XMCT measurements, synchrotron-based experiments, they show that with a nickel concentration, this is 0%, and then how the outer plane magnetization loops, how they change with the nickel concentration. And with the anomalous Hall resistance also, basically two things were concluded. One is that the perpendicular magnetic anisotropy is suppressed, and also they have seen a decrease in the Curie temperature. So this is also verified with XMCT measurements, and you see that I don't have time to go, but with the XMCT signal as a function of the concentration of nickel, you see that the signal changes, and also the magnetic moment that also changes with temperature. So basically, by these two methods, they have come to this conclusion. Now the question is, why does it happen like that? So they came to us, and then we did a lot of calculations to simulate this alloying part. And basically what we see that the A-axis and the C-axis lattice parameter, they also change with nickel concentration. And also all the local properties, they were also looking at local magnetic moments and things like that. They were extracted. But the important part is actually the magnetic exchange interactions. So what I am showing here, this is the pristine FGT where there is no nickel atom. So what I am showing here is the isotropic exchange parameter as a function of distance between the pair of iron atoms here. So in the inset, you see that the first neighbor interaction, this is very strong ferromagnetic. Plus means it's a ferromagnetic exchange, very strong here. And then you have, then the expanded part is shown here in this plot. So you see that there is an oscillation between ferromagnetic and antiferromagnetic exchange here. But the interesting point is that when you have nickel doping, the nickel can go to a substitutional site, and nickel can also go to the intercalation sites in the van der Waals gap. You see you see different types of exchange interactions with all the different pairs present in the system. They are plotted here. So you see, along with all the positive numbers, you see a lot of negative parameters, the antiferromagnetic exchange parameters, they occur. And as a result, if you sum all these exchange parameters, then you see that the resulting effective exchange that decreases, and also if you do a Monte Carlo simulation, the Curie temperature also decreases. So basically it follows the experimental observation, and then you can look into the magnetic anisotropy. By magnetic anisotropy, I mean the magnetocrystalline anisotropy that comes from spin-orbit coupling. This is what we can do. We can do an atom-resolved magnetic anisotropy, and if you look into that, this is the pristine system. What you have a plus here, meaning this is out of plane magnetic anisotropy, and minus means this is in plane magnetic anisotropy. So most of these atoms in the system, there are two layers. This is the one monolayer, this is the second monolayer. You see that all of them are carrying magnetic anisotropy energies, local magnetic anisotropy energies. But when we dope with nickel, then you see a lot of things happening. First of all, this magnetic anisotropy, which was out of plane, they become weaker. And also you have these atoms in the van der Waals plane, they show the opposite direction of magnetic anisotropy. So if you sum them up, what happens is that the total magnetic anisotropy, which is still perpendicular, which is decreased significantly compared to the pristine system. So basically I said that there were two things. One is the suppression of the Curie temperature, and the second one is the suppression of the perpendicular magnetic anisotropy. Both of them we could show by nickel doping. So this is good. Then I come to the proximity effect. Okay, now we have the same system, iron 3 germanium telluride system. So can we generate some skyrmions here? First of all, I told already that this is a centrosymmetric system, so we cannot expect to see in a pure system like that. So we thought that, okay, let's take a material like hafnium ditelluride, which is also synthesized two-dimensional material. It has a high spin orbit coupling, and let's see whether this proximity with the iron 3 germanium telluride, whether that can make any difference, that can do something extraordinary. For that, we do the same things, the DFT calculations, and we calculate the atomistic parameters, and then these atomistic parameters can be converted to micromagnetic parameters with this formula. Basically, you need the exchange stiffness and these D vectors coming from Zaloshinsky-Moria interaction vectors. So you can take all these things, and for these two systems, they are actually listed here. You see the D value is completely zero for pure iron germanium telluride system, whereas you have certain small value here for this heterostructure. But then with all these parameters, if you do the simulation, micromagnetic simulations, you do not see any signature of skyrmions. Because I said that these parameters must work together in some specific ways if you want to see any skyrmionic formation. So next we thought that, okay, some people have said that maybe the FGT systems, they're oxidized, and that's why you see the skyrmions. So we had a model here with some oxygenated part here. And then we did exactly the same things. We calculated the parameters and we did micromagnetic simulations, but still we did not see these things, any skyrmion formation. But then finally, there was one sweet combination when we have a bilayer of this iron germanium telluride, which was oxygenated like this, and we have this hafnium ditelluride. Then we see that your D value actually increases, and the K value, the uniaxial anisotropy, that also decreases. And then it gives a nice combination. Then you certainly see that there is a formation of skyrmions. And you see that another interesting thing is that you can see the formation of skyrmions even at zero applied magnetic field. And when you apply a magnetic field, then finally at 2 Tesla, that disappears, so you do not see the formation of skyrmions. So anyway, so this is a hypothetically designed heterostructure combination where one is able to see the formation of skyrmions because of this sweet combination of all these parameters in your spin Hamiltonian. Okay, I do not have much time, but the last part is the high throughput prediction of 2D magnets, and this is a lot of different groups nowadays. They are very much active in finding new magnets, proposing new magnets, and then we also started doing this, forming an automated platform for high throughput DFT calculations, and specifically the magnetic properties. What we want to have an automated big data generation for new 2D magnets. And as I said, iron 3 germanium telluride. So our first idea was that if you replace germanium and tellurium by this block from the periodic table, then what happens? So then when you have so many different compounds, you have to study certain stability criteria. So we have certain stability criteria. This is not a complete condition for stability, but nevertheless we have we look into some entropic some enthalpy consideration. So phonon calculations, dynamical stability, mechanical stability, and also thermal stability at high temperature, whether they're stable or not. So from 529 compounds, we came to around 31 stable compounds. And then there are, all of them are listed here, all the 31 compounds. So this block contains materials with high spin magnetic moments, and some of them are synthesized already. They are listed here, orbital magnetic moments, and their corresponding data, different data like magnetic anisotropy energy and everything is there. So now it's time to calculate the magnetic transition temperatures, and there is a plot with magnetic transition temperature against the exchange stiffness. Both of them are interesting parameters for experimentalists. So I want to highlight only two materials from here. One is at iron 3 gallium I2. This, you see a collinear magnetism here, very high Curie temperature. But on the contrary, this iron 3 selenium I2, which at T equal to 0 Kelvin, which shows a spin spiral structure. So you can see a variety of magnetic structures in this study. And if you look into the iron 3 arsenic bromium 2, you see some Neal type of skyrmions. They also appear. Now, the whole idea of studying this is to motivate experimentalists whether this is at all possible to synthesize. First of all, this is the first step, synthesize these materials, and then to see whether these properties can be studied. And in the last 2 minutes, we also looked into another type of, chemical composition, iron XZ2, following this particular material, iron niobium tellurium 2. This niobium, they come from the 4D series with high spin orbit coupling and things like that. So we wanted to study that what happens if we replace this niobium by other with tantalum, for example, niobium, tantalum, and these chalcogens can be sulfur, selenium, and tellurium. And so all this combination of materials, they pass the stability criteria. So that means we can go and we can look into the magnetic studies. Nevertheless, one small point is that this particular material actually crystallizes in two structures, orthorhombic and monoclinic. Orthorhombic shows a spin glass phase, and monoclinic shows a ferromagnetic phase. So we concentrated on that. And I don't have time to go through this analysis, but now you can analyze the exchange interactions through the different type of orbital resolved exchange parameters and the corresponding hopping between different orbitals. So this kind of analysis, they exist here to understand that why certain interactions are ferromagnetic and why certain interactions are antiferromagnetic. So I skip this one. Also, another thing emerges here, that the magnetic and the easy axis of magnetic anisotropy is a tilted one. So this also is another feature of this kind of magnets. So both for iron niobium telluride and iron tantalum telluride, we see some kind of tilted magnetic anisotropy feature, which can be interesting for some experimentalists actually. And one of the variants is the Yanu structure. Then you have a selenium and tellurium in the opposite sides that breaks the inversion symmetry, and you can expect to see something like skyrmions here. And definitely we see the presence of Neal skyrmions, which also happens at zero applied magnetic field. So which can also be interesting for some experimentalists. So now I come to the conclusion. So I have talked about iron germanium telluride, iron 3 germanium telluride, which is a centrosymmetric two-dimensional ferromagnet. But when you put nickel into it, some of the nickel atoms go to the substitutional sites, substituting iron. Some go to the van der Waals gaps, and then there is a certain combination by which you can actually decrease the exchange parameters and the perpendicular magnetic anisotropy. These people haven't looked into the spin glass physics yet, but I am also sure that something will happen in this material also. Then this was a prediction of proximity-induced fermions if you have a certain design with heterostructure. And then we have predicted certain new two-dimensional magnets following some of the synthesized two-dimensional magnets, and we show some interesting properties of these materials waiting for the experimental synthesis and characterization. I will finish here. Thank you very much.
Thank you. Questions, comments?
Hello, sir. Very nice to hear you.
Thank you.
So my question is the slide where you discussed about this magnetic exchange interaction. So you can you go to that slide?
There are many slides. Which one do you mean?
Where you talked about the interatom distance and the exchange parameter.
Okay. Maybe you mean the first project. Yeah. This one? Yes, please.
It is changed.
Oh, sorry.
Thank you. So here, as you know, this iron germanium telluride had two types of iron atoms. So these are, which iron atoms?
The highest one is this, the one that you see in the inset. You see this 90 milli-electron volt, this the big one. That is the iron 1 and iron 2. This between the central part and the outermost part. Yes, yes.
And the antiferromagnetic is shown by the 1, right?
Yeah, yeah.
3 plus and
Yeah, that much should be. I don't remember exactly, but I should have actually designated them pair-wise. But this is a combination where you see everything here. But the highest one, that is that one, because that has the smallest distance.
Okay. Thank you very much, sir. If I'm allowed, I have one
No,
quick
please.
question.
Later on. You can discuss with him.
Yeah.
Thank you for the wonderful talk. I have a question from the last part of your talk where
Yes.
you mentioned this iron-based 2D magnets,
Yes.
high throughput calculations. Is it based on graph neural networks or something else?
No, this is pure DFT calculations. We have just generated data for new magnets. If you want to do something with machine learning, this is the ideal thing. Just ask for the data from me.
Okay, thank you.
This is pure DFT calculation. Lot of databases are there. We didn't want to choose their system. We wanted to generate our own data. That is the thing for it.
Okay, it was a very good talk.
Thank you.
I just need one clarification. So when you obtained the skyrmion, that was basically jacking up the DM interaction, right?
Not only that, reducing the anisotropy also.
Good, but you also mentioned that these systems are centrosymmetric.
Centrosymmetric in the pure phase, like iron
But
3
once you start doping, then...
Yeah, you break. Even if you break with oxygenation, you don't see skyrmions.
Okay.
So there must be something else happening in the actual real system.
Good.
Yeah.
Professor Sanyal, thank you so much. It's very fantastic,
you.
how theoretician and experimentalist they touch to each other. That's always the European think about it. That's impressive. Anyway, I'm still trying to absorb, or try to convince myself that the underworld magnet for you such a periodic 3D system. How do I expect, because your iron 2 sublattice is also having covalent bond with the neighboring other germanium. I would say layered magnet, not van der Waals layered magnet.
No, but the layers are coupled. Each monolayer, they are coupled to each other by van der Waals exchange interaction. Within a layer, all of them are covalently bonded atoms.
The green color iron atoms are itself having another covalent character. So, van der Waals could be the heterostructure, the second part you discussed. But anyway, I try to convince myself that
So
yes.
now this is a very new thing. No, your question is not so bad. I mean, it's a good question because the moment they are intercalated, then there are some bond forming. That's why I would say that these are two different species acting at the same time. One within the layer and one across the layer via this. So the microscopic mechanism has to be studied, which is completely unknown right now.
Anything? If there are no more questions, let's thank him again.
Thank you.
Our next